Subrata Chakraborty is the lead writer of a new paper that attempts to explain these differences. He's also a professor of chemistry at UC San Diego. Welcome, Dr. Chakraborty.
Hi, it's great to be here.
So, tell me about the discrepancy that was noted in the meteor that fell 40 years ago in a stony meteorite that exploded over Pueblito de Allende, Mexico.
Yeah, that's interesting thing is that oxygen isotope usually sort out according to their masses. So when this meteorite back in 1973 was found and analyzed, surprisingly, it was seen that the oxygen isotope in that meteorite has not been sorted out according to their masses, what we see for Earth and the other rocks from the terrestrial planets. So that was a kind of discovery, and that put us in this field that why this oxygen isotope of the meteorite is different. And afterwards, there are lots of measurements which shows that is not a fluke. All the meteorites, especially the meteorites which carries the primitive minerals, has the oxygen isotope which has not sorted out according to the masses.
Now, does this difference manifest in a way that we can see them? Do they look different? How does it work out, this reordering of the oxygen?
So in our field, we measure the ratios of different isotopes of oxygen. And when you have this measurement done, they are really show up in a different space in a plot. So the oxygen isotope from the terrestrial planets are grouped in some place, and the oxygen isotopes from the meteorites grouped in another space in that plot. So that's how we can see how they are different. Like Earth, Mars, Moon, all lie in a one space in that plot, and the meteorites in the other space, totally different grouping.
Now, it's interesting that you mentioned Mars, because I was just thinking that a few years ago I was in the Air and Space Museum, and I got to hold a piece of Mars that fell to Earth in about the 1920s. However, they didn't discover that it came from Mars until the mid-'70s, when the first Mars rovers landed, and they were able to do gas analysis, and they discovered that the gas trapped inside the meteorite was the same as what came from the red planet. And so I'm wondering, in this case, in the case of this oxygen, should this be surprising? Don't rocks always form based on the particulate matter that's immediately surrounding it? Yeah,
that's a very surprising thing that all these rocks form from the solar nebula, and why these rocks in the Earth, Mars are nearly the same, and why these meteorites are totally different. And if you want to understand this, we have to go back in time. Like, most of the meteorites come from asteroids, and a lot of asteroids are primitive. That means they have not gone through secondary processes like Mars, Earth has gone through. So they preserve the very primitive signature in some of the minerals. So when we get a meteorite from an asteroid, and if that is primitive, it has that mineral which formed 4.6 billion years ago. So we get the history from this meteorite from the starting of our solar system. These rocks tells us what's the difference between the formation of the terrestrial planets and these other rocks.
But you said that all meteorites seem to have this pattern as well. So is it not just the rocks that were formed 4.6 billion years ago, but a condition of how rocks are formed in outer space?
The further processing, we lost the signature of that particular thing in further processing. Like our Earth has gone through melting and differentiation, we form the core and the mantle and the crust in the rock in our own Earth. But these meteorites, some of the asteroids, has not gone through this processing. So they have this primary signature intact. So that's why we don't see them in Earth's rock or the Mars rock, but we see them in the meteorites.
And so in order to get a better picture of this, you decided to try to create a model of the conditions that may have existed around 4.6 billion years ago, fairly soon after our solar system began.
Yes. That's true. Like, if you see the thing in this perspective, that our solar system formed, and we have this rock or the minerals which are stored in this meteorites, and they have the oxygen isotope totally different. And oxygen is the most important or the major rock-forming element. And we need to understand that oxygen distribution to understand how the chemistry or the processes in the early solar system happen. At the time when this discovery of this Allen meteorite happened in 1973, we don't have any idea that any kind of chemistry can give isotope distribution or sorting of isotope according to non-masses. As I said, oxygen isotope usually sort out according to their masses. And these meteorites, they don't follow this. And we don't have any explanation that or any demonstration that chemistry can do that. In 1983, we have a paper by Mark Timmins of UC San Diego. He showed that in a ozone formation process, we form ozone where the oxygen isotope in that ozone doesn't sort out according to their masses. So that established chemistry can do it. But you don't have that much of ozone in solar nebula to explain the findings in the meteorites. So another thing came is that photochemistry can do some kind of effect. But back in 2008, we published a paper in Science showing that photochemistry can produce a lot of effect like that, but those effects doesn't match with that of the observation. So our whole community was in a kind of in a situation. There is lot of measurements, lot of data, but we don't know how to explain them. And that was like driving me crazy since last several years. And we are finding out what is the best way to do this thing. And then we came out with this idea to represent or simulate the nebular condition in a laboratory.
So you decided not to build a better mousetrap, but to rebuild the solar system from scratch in a box.
Yes.
What did you put in that box?
So this is a very small chamber. And, hydrogen is the most abundant molecule. So we put hydrogen, and we need to do a gas-phase reaction we are thinking of. So in the solar system, we have gases and also the dust. So we need to put dust. So how can we produce dust? So what we thought is that we'll create the dust inside in situ. So we put some silicon monoxide, which is a very refractory molecule, which is a solid species, and we bombarded that SiO with high-intensity laser beam. And we generate a plume of SiO as if we are producing gas inside a nebular environment where we have oxygen and hydrogen, and allow these to react and form solid silicate. We formed SiO2, which is the simplest form of silicate. And we collected that SiO2 as if they are the solid first form from the gaseous nebula.
And so you brought all these materials together. Did you also try to simulate other conditions, temperature, gravity?
Those are in our next thing, but we really did some simulation experiments, and we saw a variation based on temperature. And rather, we are doing much more right now. And we have not touched upon yet about the gravity part.
So you put all these materials, though, in the box. You didn't play with gravity. You did play with heat to a degree. What came out? What did you find?
Yes, that's interesting. The solid which formed in this condition, like solar nebular condition, we formed these rocks. And when we measured the oxygen isotope in the rocks, we are like mesmerized at the beginning. Wow, it has the same isotopic composition as we see in the meteorites.
So you effectively recreated an early moment of the solar system and generated similar results.
Yes, that's the exciting part of the whole study. That's why it's in Science.
And so where does that lead you? What does that change in terms of our understanding of the universe, of these rocks, of all the materials around us, possibly even of Earth?
Yeah, because chemistry is like we proposed in this experiment, like SiO reacting with OH, forming this rocks which has this effect. Now, we have this OH observation from all these astronomical missions, and these reactions are very important. It is not always the condensation of gases to form solid. This is a basic concept, like everything condenses and from the gas phase when it is hot and then cools down and forms particles. Apart from that, we have a lot of chemistry going on in the nebular disk, and this is a proof of that, of chemistry.
And how much variation did you find within the chamber? Were there different materials made in one side of the box, different towards the center, different at the other extreme?
Yeah, we found a percent level change, more than a percent level change inside the chamber. Our chamber is too small, but even though we see isotope effect at the center and at the side of it and at the top of the chamber. So it is like a small spatial gradient inside the chamber, and that's another implication that chemistry is going on, and based on the local condition, the chemistry differs. And this is very true for nebula. A nebula is not homogeneous totally in that sense, and it has different pockets, it has local density difference, temperature difference, so different kind of chemistry. Same chemistry, same reaction may result in a different isotope effect when you consider the whole nebula.
I want to ask the Thomas Edison question. Thomas Edison famously invented the light bulb 100 times before he actually invented a working light bulb. Mm-hmm. So I want to ask, how many times did you have to vary the ratio of ingredients within your chamber before that you got this reaction and began producing the rocks that had the effect you were looking for?
Actually, if you say so, it is a long time effort. I was trying with 7 or 8 different types at the beginning, but everything was kind of not working. Then we are actually working with another very important project, which is called Genesis mission, which is a spacecraft sent by NASA in 2004 to collect the solar wind sample. And our job assignment to measure the oxygen isotopes of that solar wind. Because we know, we are talking, all are related. We are talking about oxygen isotope, and our solar system mass is concentrated on the sun. 99.9% of the mass is the sun. And we are talking about the oxygen isotope variation between this planet and the asteroid. But what about the sun? What's the composition of the sun? We really don't know. So this spacecraft was designed to measure what suns look like. So in this process, we are developing an instrument to extract these atomic oxygen from the solar wind collector. And the process we are using is a laser kind of excavating atoms from a substrate. And for doing that, we have done experiments for last 5 years and established a lot of parameters which are important to work with a laser plume. And that actually helped design and do the experiment much quicker. If we had to start from the beginning, it would have been 7, 8 years. But since we are working in the other project, which is very close by related, we learned a lot about the plume chemistry from those experiments when we applied directly to this particular experiment we are talking about.
So like in most fields, every overnight success takes years in the process and is built upon a foundation of other research, other ideas, and the development of unique technologies to help it along.
Yes. This is another example of that.
So, final question.
Yes.
What's next? What is the next thing you're out to prove or to re-verify?
So the thing is that we have done the simplest, most important thing, like forming the simple silicate, SiO2. But if you see all the rocks, they are more complex. They have all other elements like chromium, iron, and everything inside. So we need to form more complex element and see how this element changes the isotopic composition, or how is oxygen independent or they depend upon other element. Like if the more amount of iron is present, how that behaves, how the chemistry goes.